Oh, okay, I see. Okay, so should we start? Let's start, right? Okay, so I'll go like through questions in order, and if you have any questions, please ask. Also, if you run out of questions before the end, if you go through the whole exam like on time, like I'll also give like a few of my own questions, like to just some clarifications on the course content. Also, because like those like this is just a past exam, and the Rukmi didn't give answers to it, and so all of my solutions which I give are accurate to within ambiguity of the questions. So don't rely on my answers to be like 100% correct the way Rukmi wants them to be. Okay, so first question. So essentially we have two one. I probably need to have two lines made of conductor, and we know we're given they have a radius a and the distance between is b. D. So and the first question asks us to show that it is equal that electric field is that's for d much larger than a. From here, from d is larger than a, we can assume two things. First, that we can ignore the effect from them being made of metal. So we don't need to use metal images basically. And second, basically yeah, like this yeah. So yeah, I'll just show the derivation and then explain it. So electromagnetism is linear, and it is true here because we are ignoring method of images in this case, because those two conductors are made of metal, and metal technically is non-linear, but we can ignore it here and assume that those are basically just rods of charge without any metal in them. So this means what we can do, we can just take one conductor, one rod, analyze it separately, then take another one, analyze that separately, and combine the results. So we take just one rod of radius a, and we take some radius r from it, right? Assume that it has some charge density rho l, right? Then we know that electric field. I'm just going to delete this. Yeah. We know that from Gauss's law, if you take Gaussian surface around it, at radius r, we're going to have that 2 pi r, the magnitude of E, is equal to rho l on epsilon naught, right? Yeah. What image? No, we are not, because we can assume that D is much larger than A. But it will come later, right? At the moment, we're not using method images, and as I said before, I highly doubt that Rukmi is going to ask you to do method images on curved surfaces in the exam. Like in this case, essentially how method images works, I'm just going to explain it quickly. You have two metal surfaces, right? And it essentially works as a curved mirror. You basically deflect one charge inside the other, and like this. So you end up with two smaller things. And then you continue doing this until you end up with basically 2-point charges, which are going to be offset from your from the center of the spheres, of the cylinders, by some call this b, and then you need to find the value of b such that at the surface of the conductor potential is the same, basically. And then you need to find the value of potential at every point, then sub it in this all this r dash, and this point is going to be this is going to be r dash cosine. Sorry, this is in this case it is a cosine theta squared plus a sine theta squared, and then this from this point is z minus b basically, and so you solve the whole thing you solve this equation with cosines and sines, and you have to say you have to have that for any value of theta, potential is the same basically. This is piece involved working out, and so like I don't expect in my Rook is going to force you to do it in the exam. I like in the and here he just gives you the formula and wants you to compare it, right? So like I don't think you have to do it in the exam, but it's not really hard, just very involved and very long. Okay, so to continue with this, essentially we just take one charge, one cylinder of charge.
Pardon? Oh, network.
10 because our D is exactly 10 times larger than A. So D is equal to, I think, 5 millimeters, or 5 centimeters, and A is 0.5 centimeters. So our log is exactly log 10, which is roughly equal to 10.86 kV page. Then our E at 0.1 is going to be equal to that constant 10.86 times 1 over A plus 1 over D minus A, which is roughly 2.413 megawatts per meter, right? And it is actually going to be the same E at point, that is 0.2, 0.3. At 0.3, we are going to be the same answer. Why? Because the situation is symmetrical, as I said, 2.413 megawatts per meter. Our E at 0.2 is going to be just in the middle point. Our 1 over R plus 1 over D minus R is going to be, it's just going to be twice times half D. Because it's like, because our R here, R is equal to 1/2 D, D on 2. So this is going, it's just going to be 10.86 times 2 over, 1 over D. Because it's 2 over D times 2, and this is going to be something like 0.0869 megawatts per meter. And if you draw it, this is our magnitude of E, our R, the middle point, D on 2, this is A, D minus A. We're going to have something like that. Here, going to be equal 2.41 megawatts per meter. And here, the minimal point is 0.869 meter. Good. Now, I wanted to point something out. If you look at this, there's a quick rule of thumb, if Rukmi asks you a question about breakdown, breakdown voltages, normally for flat planes, if you have two flat planes, it's kind of like a general rule of thumb. And the breakdown voltage between those plates, if they have the two infinite particle plates, breakdown voltage is roughly 30 kilovolts per millimeter. So you see kilovolts per millimeter. You need 3 kilovolts to break down 1 millimeter. right? But here the surfaces are curved, so for curved surfaces we actually need a bit less because of that effect, because of log like whatever, like radius effect. And here you can see it's pretty close. So in this case, if the air is slightly humid, the conductor is going to break down. Just in case, like that's just an aside, in case Rook may ask this in the exam, to kind of like have a kind of intuition about how much voltage you need to break down something. So in this case, like these conductors are close to being broken down, from the voltage between them. Okay, then yeah. Okay, and then it asks us like to show the capacitance for D larger than A. Just going to make a new page. We know that capacitance is defined as Q over V. In this case, it is our rho L over V is capacitance per unit length, farads per meter. We know that V is from above. It's this one. It's rho L over pi epsilon naught ln d on A. This rho L over pi epsilon naught ln d on A. So rho L over V is just 1 over Z. We get ln d on A over pi epsilon naught. I think it is the same as they wrote. Yeah, same. In units of farad per meter. That's that capacitance per unit length. So 1 meter of cable has that much capacitance. And then we are given the formula for the same capacitance, but found using method of image, using the thing I explained earlier, where you have two conductors, you reflect them to basically a point, and then you find the capacitance from those 2 points, right? And the formula you get is here. It comes from the fact that the points will be offset from the origin by some value b, which you need to find for each value of d and a. Okay. We don't need to derive it here. We just need to compare the capacitance for the real one and the approximation from here. And so if you do that, I'll just give you a small table for we are given 2 values of d. For d equal to 5 centimeters and for d equal to 1.1 centimeter. If you look at this value, you know that a is equal to 0.5 centimeter. So in this situation, we get two pretty spaced spaced apart like rods, but here they're very close together. This is like 0.1 centimeter, and so basically this in this case d is much larger than a, but here d is actually quite close to a. So for the first case, you're going to get I have the values here. Actually, I'm just going to omit pi epsilon naught, just give you the values for in terms of pi epsilon naught, because you don't actually need to do the calculation to find the percentage error. So for the first case, your C approximate is going to be 0.4343 pi epsilon naught, and the C actual is 0.4362 pi epsilon naught. You can expand it in compares, but it doesn't really matter for all calculation. The percentage error is C actual minus C approximate over C actual, which is roughly 0.44%. Right? If we do the second case and we do the same thing, we get that our C approximate is 0.78 something pi epsilon naught, and C actual is actually going to be pretty close to the previous value, 0.44 something pi epsilon naught. And percentage error you get is somewhere on the order of 70%, 77.8%. One is much larger than the other. And that's because when you have like the next question, let us to explain why there's such a large error. The reason is because if you use like your just like the approximation, you basically have to like you approximate those as point charges basically. You convert them to point charges which are distance d apart. This is d and this is also d. This is approximation. But in reality, what happens is that those points are going to be reflected off further from each other, and you end up having distance of those are the centers. This distance is d, but the charges are going to be actually this is going to be d plus 2b, where b is the offset from the center, from the origin, because of method image, because of the reflection of the charges across the sphere, across the cylinder, and that's why in this case you see approximate and see actual. This is much larger than this one because you have charges which are effectively close together. And actually, if you have a look at the formula, because log of something close to 1 has a gradient of 1, and from that you can conclude that this actually approximates the formula for the particle plate capacitor, which makes sense because if you zoom in, if you have two cylinders very close together, if you zoom into this region, this basically looks like a particle plate. And you can find that the formula approaches that as you have your spheres closer and closer. Anyways, it's just an aside. But the explanation is given here. That's the question, the next part of the question. It's this one. Comparing the percentage error found and conclude that the center centration has error cases, and we need to explain why this happens, and have just given you an explanation for that. Any questions for this part? I think that's the end of this question. If you need any clarification, ask now.
No? So it's just the error rate metric of
Yes. Yes, because if we assume that d is greater than a, we still continue using the same approximation of point charges, where they're no longer point charges relative to the distance to each other. And then you have an effect that effectively they the centers of charge move apart relative to the centers, because the conductors, they have an induced surface charge to cancel out any field inside of them, and that in effect has this causes a reduction of overall charge on the surface. So you have actually a smaller capacitance than you expect to have based on the simple approximation. Essentially, yes. Essentially, the approximation breaks down, and you can no longer use it. Do you have so far? Do you have any requests for what questions I should do next? Because this is basically the same kind of electrostatic problem as before. Yes, okay. This problem, it's not actually on magnetism, it's about virtual displacement. I think self-inductance, then okay, yeah. This question is a bit vague. I will explain why later. But let's go through it in order. So new page. Question 3. We are given. We have a situation like this. We have a big iron core with some coil on it with 5,000 turns. I'll probably zoom in a bit to make it to save space. And then case diagram. We have our size is 0.1 meter. 0.1 meter. And then here we have a bar which is spaced by 5 millimeters. And actually we'll call this D. This is called D. And this distance is also 0.1 meter. The cross-sectional area of this is 0.02 meters. Sorry, I'll just write this like this is like 2 centimeters and 2 centimeters on the side. So, and what the question actually asks us is to find the work done by the magnet to pull this thing to itself. It's essentially like a piston, right? We have like this moving bar, which we are going to try to push, like try to attract, like to our magnet in a kind of actuator, like system. So first, first question asks us to explain the virtual displacement principle here. So we know that our force is equal to gradient of work, and it's plus because our current is constant. We have current I going through. The question is, like group me define this as just gradient, but it's not really like physically, like it's not really like meaningful to call this gradient. If you have like some force and you have some mass and you move it some distance d, call this no, I will call this a path length dl. This is a very small infinitesimal path length. Then your work done is f dl. Actually, this is dot product because both are vectors. Then your d work is going to be actually this is d work. Yeah, sorry, I'm working with in some decimal quantities. Then your force is going to be d work over dl, which is a vector, which is the same as gradient of work times dl along some path lengths. Mathematically, it makes sense, but logically, you can't really take a gradient of energy. It's kind of a physically meaningless quantity. So usually you just take if you have some displacement d, then you take your work, like the derivative of work of L I squared, correct? And as we are given the dimensions of the core, we can find L as n squared over reluctance, R recursive in this case. Then we are given the formula for reluctance in the formula sheet. I'm not going to look it up. I have it on the paper written. You don't need to remember all the formulas. Questions here, right? Yeah. Questions here. So reluctance, our reluctance is the sum of reluctance of the core plus reluctance of the air gap. And reluctance is given as length over mu area. So it's for the gap, S gap, mu naught plus L core over S gap, which is the same for the core and the gap, is the same rotational area, mu r, mu naught. Which this one is 2D, this one is 0.4 meters, because you have 0.1, 0.1, 0.1, 0.1 all the way around. This one is 0.02 times 0.02. It's a square area of the core. And this one is given as 1000, I think. And so you end up, if you do the math, you will end up with two things. You will end up with the constant reluctance of the core and reluctance of the gap dependent on d. So that's like 4 times 10 to the 9 d plus 0.8 times 10 to the 6. It's just a constant offset because of the core. You can see that the one for d is much higher because air is much less reluctive than metal, than iron. Then our inductance is n squared over reluctance. And actually, if we do it, we get n squared is like n is 5,000, we get 25 to the 6, I think, over that's in from here. And actually, if you calculate this at d equal 5 millimeters, we get 1.202 Henry at d equal to 5 mil. And this is going to be useful in the later part of the question, because later we asked to find inductance, yes? S, it's area of the core, a cross-sectional area. Like you have like, yes, it's the cross-sectional. If you cut the core across, you're going to see like a square like of metal, and that's the area of the square. It's this part, right? Yes, we're going to need this later on, but at the moment we're not going to use it. Our force along D is going to be D work dd. It's really bad notation. I probably like, yeah, yeah. I'll just go this D capital because dd is not nice. And this is going to equal 1/2 I squared dl, d capital D, because our current stays constant in this case. And our L depends on D, as we have some constant plus 4 times 10 to the 9 D. And if you do this, we get 1/2 I squared times, if you do derivative, we get minus 25 times 10 to the 6 times 4 times 10 to the 9 from down here is this one. And on the bottom, we get the same thing, but squared, 0.8 times 10 to the 6 plus d times 4 times 10 to the 9 squared. And if we evaluate this at d equal to 5 millimeters, we get minus 1.156 newtons at d equal to 5 mil. The sign is negative. What does this mean? That means that our df, our f is opposite sign. Our f is opposite to our change d. That means that if we try to pull it apart, the force is going to be opposite to the change in d. That means we are trying to pull our bar to the magnet, right? So the force is trying to close the gap logically, because our direction of force is opposite to that of displacement of our differentiating factor d. So the magnet is trying to pull this in with the force of 1.16 newtons. If this were positive, it would be pushing it away. Yeah, okay. I think I have done most of this question, but now I have done this. Okay, self-inductance. Assume for like self-inductance of the coil. I have already done this. If you remember, I found inductance here, and this is basically the answer to the next part. It's 1.2 Henry. Now, if you look at the next question, if coil supply 50 Hz AC, current 0.5 amps, find the RMS value of supply voltage. This is just your 2134 material. You have a voltage source. Sorry, that's a voltage source. It's at 50 Hz. And you have a coil. And you know the current is I is 0.5 amps peak, not RMS. I know that the voltage is just I times magnitude, that's also magnitudes, times impedance of inductance, and this is just your I times 2 pi f L, I think. And this is like 1.202 Henry. This is 50 Hz. This is 0.5. So magnitude of V. Actually, I want VRMS. We ask for VRMS, which is just magnitude of V over root 2, which is roughly I think it's 100 something, 133.5 volts RMS. Okay. The next part, it's a bit ambiguous because we asked AC supply causes eddy current loss in the core. If the eddy current loss coefficient is Z, the total eddy current loss in watts. Okay, so here we need to assume either that current stays the same as before or voltage stays the same as before. That means that we either supply our thing with a voltage source or a current source, which is not specified. And the reason for this is because if we do the same thing, if we just carry this over from the previous part, now we have an inductance in series with resistance. A resistance comes from eddy loss because now we have an actual loss of power in the core. Now we have eddy currents, and we have some resistance in series with our inductance, which we don't actually know before we calculate the equation. So either if we set our voltage to be 133 volts, our current is going to be less than 0.5 amps, or if we set our current to be a current source, we have 0.5 amps, but our voltage is going to be higher than 133 volts. This is going to be above 133. I'm going to go with this one because it's easier to calculate. Because in this case, you have to actually go from current, find the value of B field, magnitude of B field, and then go from there. Actually, out of for sake of completeness, I might go through each case. But first, I will go through this case because it's easier to work. Yes, we know that I just separate this out into two sections. This case 2, this is case 1. I'm just going to go through case 1 first. Our eddy loss is some coefficient F squared B magnitude squared. We know that B magnitude is flux magnitude over area, and our flux magnitude is V over 4.44 Fn. We are given this formula in the formula sheet. It's just basically 2 pi something n, some constant n, epsilon naught I think or something. And then if you sub it in, we get a Bm is equal to 0.3 Tesla roughly. Here our V stays constant. We set our V to be a voltage source, right? And then from there we find our P eddy to be 27.13 watts roughly, which is a reasonable value in our case. Now look, as before, if you have an actual inductor, an actual transformer, and connected to AC mains, right? If we are going to set the voltage, our voltage is going to be fixed. It's going to be like here we can just use V. V is a constant. The current is going to change based on our loading, right? If you have eddy loss on, don't have it. But if somehow we adjusted the current, then we're going to go a different scenario. Essentially, here we need to find Bm as a function of current, not a function of voltage, because we don't know what voltage is anymore. And okay, so what can we use in this case? We are given how can we do this? Okay, so Bm, we have our core. Bm is going to be flux over area. Flux is going to be our reluctance times Ni, correct? Which is our yeah. Sorry, yeah, you're right. Yeah, it's like the same analogy as as with Ohm's law basically. So your Ni over reluctance is flux. You know what I is, you know what N is, what R is. Then you can find, actually I haven't done this like this working out by myself. I have done this, so I have the numbers, but here I haven't, so I don't have the numbers. So essentially I'm just going to write everything symbolically. Our F is Z, so our Bm is Ni over S, and because this is L over epsilon mu naught, sorry, mu something times S, this S cancels out essentially. So this becomes Ni over our R is now L over L. This is our D to D over epsilon naught plus L core over epsilon R epsilon naught. Sorry, like mu R mu naught. Then this is our BM, and then our like we sub this like this value into our formula for PE. PE is Z times some coefficient KE F squared, and then N squared I squared, and then this is squared. This is 2D over mu naught plus LC over mu R mu naught. And if you plug this into calculator, you get a different value. And I think in this case it's going to be higher. This value is going to be higher than this one, because in this case we have half num, and the voltage is going to be higher than 163 volts. But I don't have the value, so I have calculated it before. Like this is just like the symbolic formula for it, which you can like calculate yourself if you're interested. I think that's it for this question. Yeah, so this part is a bit ambiguous. And in the exam conditions, I think what you're supposed to do, you're supposed to assume that V stays constant or that I stays constant, and do it like the way you wanted to do. Like as long as you write that you assume something, I think it should be fine. But again, like it's like the question is ambiguous. Do you have any more requests for what question I should do next? Yes, that's end of part A. You have 3 questions for part A and 2 questions for part B. Question 2, okay, fine. Question 2 is basically it's very similar to question 1, actually. Yes, I'm going to do it because another part in it, like the part with like there's another part like the part where I need to calculate the resistance of the coaxial cable. And let me just find it. That's that's just this one, just one page, very short. So we are given a coaxial cable. We are given this question. Sorry, question 2. We are given a coax with known dimensions A and B. A, this is B. We have some voltage V naught between them, and we are given it has a permeability of epsilon, and I think epsilon is not given to us. No, we're not given epsilon, I think. No, this should be. I think no. Finally, it's not given. We don't have the value of epsilon. This is not provided. So I'm going to first use use it symbolically, and then we're going to find the numbers. I'm just going to assume it's air, because it's most straightforward option to use. So this is some epsilon which is not provided. So we're given Laplace equation, right? This but if you notice, this is our theta. We have a cylindrically symmetrical conductor, a cylindrically symmetrical coaxial cable. So this part becomes 0. And since it's very long, we assume there's no Z dependence, this also becomes 0. And since we get 1 over R, no, I'm going to write on the other page so that it's in one place. dV dz is equal to dV d theta is 0. And notice I'm using full derivatives because there's no Z dependence and anti dependence. So 1 over R d r dV d theta, sorry, dr is going to be 0. This becomes 0. And now we say that R dv dr, this is v, this is r. R is, yeah, is equal to constant. And now we just use direct integration. We have that v is equal to integral of 1 over r dr. Yes. From a to b. To again, I'm just going to do the same thing before. I'm going to call this r dash, and our length is going to be r. And this is equal to some constant, because here we have a constant, times ln r over a plus some other constant. I'm going to call this a and this b. Right? We have two unknowns which you need to find as well. It's just the form of our voltage between the two things. If we sub r equal to a, this just becomes 0. So like it makes sense that b is just the voltage at a, because at r equal to a, this part is like this part becomes a 0, right? Which we call v naught, because we assume that there's a potential v naught here and potential of 0 here on the shield. And then we need to have that v of b is 0, which is equal to a ln b on a plus v0. So our a is from here we conclude that a ln b on a is minus v naught. So this means that a is just minus v naught over ln b on a. So our formula for v is minus v naught ln b on a ln r on a plus v naught, which is actually v naught 1 minus ln r on a ln b on a, which kind of makes sense. Just have our full voltage and we scale it by a ratio of logs of distances. All good? Great. Then the other question. Yes, we are given value of a, value of b, a value of voltage, and we need to find the maximum and minimum values of electric field. We don't know what the electric material is. We don't know what this is. This is not given. We are not given epsilon, sorry. So I'm just going to assume epsilon r is 1, so it's air or something close to air, like whatever. Like the answer is if you want to find the answer for any electric, you just scale it by epsilon r. Basically, electric field is going to be less by the value of epsilon r. So we are given that v naught is 60 volts, a is I think 5 millimeters, 0.5, and b is 5.5 mil, b is 5 mil. So ln b on a is ln 10, as before, as in question 1. And then what we get that our Emax is E. Actually, sorry. I think I didn't finish the last question. We are asked to find electric field distribution, and I just found voltage. Let's see, turn back. I'll just move all of this down. So to find voltage, you just to find E. It's just the divergence of a divergence, or it's just divergence of voltage, and this is just like a divergence of voltage. Yeah, in this case, like this is just like dvdr basically, because like all other components cancel out, and we get should be it should be dvdr as far as I remember. Yeah, we just have del. Okay, that's like we're not given like divergence like it's like according, but as far as I remember, it's just like dvdr from memory, and then you should get that you take derivative of log basically. You take derivative of z of log. A factor 1 over a gets on top and on the bottom, so it gets cancels out. So you get 1 over a, 1 over 1 r over a. This cancels out. So I'm just going to like ignore you get your a, that's minus v naught ln b on a, 1 over a r hat. That's in the direction of r. That's our like vector of e. That's what we expect basically, because this is basically our rho L over epsilon naught over pi epsilon naught. Pi epsilon naught. So yeah. Okay then. So we know our E field, and E max is E at r equal to a, and then if we sub it in here, we get v naught over ln 10 times 1 over a, which is around 52.1 kilovolts per meter. Assuming epsilon is assuming epsilon is like 1, epsilon r is 1, then E max E min is E at r equal to b, and since we know that b is just 10 times a, this is just 1/10 of E max, 1/10 of E max, which is just 5.21 kilovolts per meter. Okay, all good. And then the next part, it just asks us to calculate. Where was I? I was here. The next part asks us to calculate, to show the resistance, leakage resistance from here to here is equal to Z. This is not very hard to do. All we need to do, we have our sin. We know that E is equal to, this is our E. E is equal to something like V naught over ln b on a, 1 over r hat, right? And also that's like the point version of Ohm's law. We have J is sigma E, correct? Then we get what's our total resistance? Total resistance is total voltage divided by total current. So R total. Sorry, I call this R. R is just V naught over I total, and it's just V naught over integral over the surface of J dot dA over some surface. So we take like a surface around this at some radius perceive r, and this is our surface. We integrate our J through the surface, and this is going to be our total current, right? And we know that our J is sigma V naught over ln b on a, 1 over r hat, because if this r hat is radial and our dA is also radial. That means that that integral is basically just going to be equal to 2 pi perceive r times J, times J basically. And our J is this n, where this is now like the radius of our surface, perceive r. So this and that cancel out, and we get just our total current, I total, is sigma V naught times 2 pi r over ln b on a r. the R's cancel out, and we just get sigma V naught times 2 pi over ln b on a. That's our total current. And then our R is just V naught over I total, which is just sorry, what happened? Where did this go? Okay, yeah, it's here. And that's just ln b on a over 2 pi sigma V naught. And it is the same as we were asked to derive. All good? And then we need to like and then the next part, we are basically just given a length of the cable. Sorry, here I forgot lengths, because that's a distance per unit length, and we just multiplied by length, basically. And we given conductivity as a number, and we need to find the leakage current and power loss. So basically, your leakage current is this one. You sub in you sub in values of V naught, sigma, and R, and ln BNA, and what you get is that at given sigma and V naught and whatever, you get leakage current to be ILK to be 0.8819 milliamps from the formula, and power loss LK is just ILK times V naught. It is just 49 point something milliwatts. Good. Any questions? And I think that's the end of this question. So to find resistance, there are two ways. You could you could first find the capacitance of of coaxial cable, and then use the relationship that RC is equal to sigma over epsilon naught or something. But in this case, it's easier to derive it from scratch, I think, than to find capacitance first. So that's it. Should we go to the next part? I think yeah, we're on time. Do you have any questions, anyone?
Actually, I'm curious something about previous the question that
Which one?
something question. Now, fighting for the electric field, how did it make the Ellen was they on A though, because that minus the 0.5 volt.
No. It should be B on A. It should be. And I think I read previously. You basically integrate you integrate your voltage from the center to to the end, and you get basically if you do A on B, you just get a minus here. You can see I have a minus here, and then you have basically okay. As minus comes from the fact that we're integrating from A to B. If you do the other way around, we get a minus. We got plus V naught on ln A on B. Basically.
Yeah.
Yes. As direction of operation here does not matter because you find A by setting your H conditions, your initial conditions, your boundary conditions. That you're at the at the outer surface you have 0 voltage, and at the inner surface you have V naught, right? And from there you find A and B in this formula.
It's just that
Yes, yes. If you have A and B, you just get rid of the minus, basically. Okay, if no one has any other questions, I will continue with part B. The more fun part. Okay, so we are given that we have this thing, and then this is it's shorted. At the input we have 1 volt, with a switch, we are given like inductance per unit length, capacitance per unit length, and we are given that the material is non-magnetic. And then we need to find I need to draw all reflections and an output current over like time from 0 to 100 nanoseconds. So this is our circuit. Here it's shorted, and on the input we have a switch and a 1 volt voltage source. And we know that this is 1 meter long, and we have our inductance is I think 100 or 250. No, it's 250. 250 nanohenry per meter, and capacitance is 100 picofarad per meter. So first, to do like before to do anything, we need to find the speed of propagation, to find like time delay along the line. Our VP, it's root L on C, and we find this as 2.0 times 10 to the 8 meter per second, or 2/3 of the speed of light. And then if you do the math, our 1 meter leads to 5 nanosecond delay. How to find this is that that tau is 1 meter over VP. Okay. And then I think yes, is it Z8 over 1 meter? Yes, it's 1 over 2. Yeah, it's 5. Yeah, correct. And then if you look at this, basically if you have like this looks like a short on one side and a short on the other side. So gamma from here is -1, and gamma from here is -1 as well. Okay. And actually, this question is a bit different from anything we did in class. I don't think we did the question like this in class because it shows you something interesting. Oh, sorry. Yeah. You're correct. 1 over root LC. I was confused with the formulas. Yeah, it's 1 over root LC. Also, your VP is 1 over root LC, which is the same as 1 over root mu epsilon. The way you can remember this is that 1 over root mu naught epsilon naught is C. Yes, it's just an aside. Thank you for pointing this out. Yeah, I was confused as to things. Okay, so getting back to our original question, we have gamma on both sides to be -1. And if we do the reflection diagram, I'll just open a new page so that we have more space. Yeah, actually, another important thing is that our Z naught is root L on C. Now this is the right one. And if you do the math, it's going to be 50 ohms. The most common value you can find. So we have our tau, we have our Z naught, and we have our our gammas. Now let's make a reflection diagram. This is our source, load, and we start here. I will propagate a wave of 1 volt and 20 milliamps. 20 milliamps because it's 1 volt or 50 ohms. That's our input impedance, like our wave impedance of the cable. This reflects with minus sign. You get -1 volt. Yeah, it's a -20 milliamps. And then actually, because we have -1 on both sides, the gammas are -1 on both sides. We get we get the if forever reflects of this is going to be 1, 20, -1, -20, 1, 20, and so on to infinity. And if you if you try to find the voltage and current at each point on the load and on the source, here the voltage is 0, 0, 0, because it's 1, -1, 1 volt -1 volt. It's this plus that. The voltages are always 0. And here the voltage is always going to be 1. Because it's 1, minus 1, plus 1, minus 1, plus 1, and so on. But here you get 20 milliamps minus 20 milliamps, which is 40 milliamps. Here you get 80 milliamps and 20 milliamps, and so on. So what you end up having, if you draw your load current over time, this is time, and this is oops, and this is I load. You end up having steps like this. Forever. The side of the step is 10 ns, and the vertical size is 40 milliamps. Is it clear why? Yeah, because the short circuit, the current grows. And actually, the next question asks the lumped element approximation. If you place this with an inductor, I've just opened a new page. If you just say this is an inductor, this is our voltage source, 1 volt, and this is an inductor of 250 nanohenry. As an inductor, your voltage is L di dt, right? Therefore, di dt is V over L, which is 1 volt over 250 nanohenry, which actually ends up being 4 milliamps per nanosecond, or 40 milliamps per 10 nanoseconds. So you essentially have the same. I'm going to draw this in different color. This is going to be your approximation current. It's going to be aligned with a slope of 40 milliamps per 10 nanoseconds, which is the same as the square steps you had before, basically. Yeah, and task to draw the approximation current and the original current. Yeah. And if you look at the current in the source, it's actually going to be offset by 20 milliamps. It's going to be something like this. It's going to be delayed by a little bit. This is going to be your source current. Because if you can see here, it's 20. Here it's going to be 60. Here it's going to be 100, I think. Yeah. So it's going to be offset by 20 milliamps at any moment in time. Actually, yeah, it's not going to look like this. It's going to look like it's going to look like this, right? This trace at the bottom. So yes, I think that's it for this question. No, there's no generating distance. It's just basically short circuit. You basically short your voltage source onto inductor. So you just use the V is L di dt, and then you just, because both your V and L are fixed, you just get a linear increasing current, basically. Okay, this is the last question. It asks to do some things on a Smith chart, which yeah, I'm probably going to go through some Smith chart matching later. After I should have the time. Yes. So now question 5. This is the last question on the exam. You have a coax of Z naught is 50 ohms. We are given that epsilon r is 4. From here, we can straight away conclude that our VP is C on root ER, which is just 1/2 C, which is 1.5 times 10 to the 8 meters per second. Because our C is like our VP is just C scaled by like root of epsilon R. Then we have a matched generator at 400 megahertz. One volt, amplitude 50 ohms, internal resistance, and on the end we have 20 plus J100 ohms. And length is 1 meter. And we are asked to find wavelengths and then VSVR of the cable. Our wavelengths in the cable is just our VP over F, which is 1/2 C times F, which ends up being something like 0.3 something. Text. One moment. I have this over here. 0.375. And we need to find VSVR of the cable. Okay, so VSVR is 1 plus gamma over 1 minus gamma, and gamma is amplitude. What's gamma? The gamma amplitude is Z load minus Z naught over Z load plus Z naught, and the whole thing is amplitude. We know Z load, we know Z naught. So we can find gamma as 0.8153. That's amplitude of gamma, the absolute value. And then our VSVR is 1 plus that over 1 minus that, and we get 9.83. VSVR is it's a ratio, it's unitless. And gamma is also unitless. Okay. The next question, using the applied Smith chart, calculate impedance, simple generator, and finally find the voltage V as the input of the cable. So, okay, I'm going to use this one. Why? Because later I'm planning to go through Smith chart matching, and because on an iPad I can't flip it around, like I can't flip the Smith chart because I can't really rotate like I can and it's easier to just use the double-sided one. And it just overall it's it's easier to use, I think, once you get used to it. So our input impedance, sorry, our load impedance, our ZL is 20, I think, right? 20 plus J100, which is equal a small z. I don't know how to write like a small z is ZL over Z naught. It's 0.4 plus 2J. Sorry, 2J. That's the normalized impedance of the load. Then what we do, we find this value on the chart. Our real part is 0.2, so it's 0.4. Sorry, 0.4. It's this one. It's this circle. And our imaginary part is 2. So this circle. So we find the intersection. It's somewhere here. This is our load impedance. Okay. And so what we do, we rotate it by the length of the cable clockwise, because we have a cable here, and it's 1 meter long. Actually, another supplementary information. Our length of the cable, electrical length of the cable, length is 1 meter over z over lambda, which is 8/3 lambda. Just write it. Right? Yeah. And which is you can round it down you can kind of it's like rotation around the circle by 2 pi. You can kind of remove any multiple of lambda from here, which ends up being 0.66 lambda, which is 2/3. But then you can also remove half lambda because half lambda factor doesn't really account for anything on Smith chart. The whole way around Smith chart is lambda on 2, which you convert to 0.16 lambda around the Smith chart. So if you draw a line from here, right, it's very like because I don't have any rules on this end. Actually, I might try to draw it like I was. Yeah. Red. Okay. Which color? Red. I'll just draw it. Yeah. This is impedance, and blue is admittance. So instead of flipping the chart around, you just look at the blue lines, basically. And I will show you how to do it later. Like as I do, like when I do like some examples with Smith chart matching. Now, well, like the examples of people who are blue-red colorblind. So let's just. I'm not sure if this is going to work. If you draw a circle, no, it. Yes, that's no. I guess I can't move the center, but like, yeah, whatever. It should be somewhere around here. Like if you rotate by, so it should be somewhere around here. And if you do it in proper Smith chart with like proper like compasses and rulers, it should be like you should have like this should be 0.16 lambda shift. And the resulting impedance here, I'm not sure actually. I'll just draw it like properly the proper point. It should be 0.3 minus 1.58. 0.3, it's this line, minus 1.58. 1.5, 1.4, 5. It's somewhere, should be somewhere here. It should be this point. So instead of drawing this, then I'll just draw it like this. Yeah. And then you draw a circle. Yeah, close enough, whatever. And so this is your output impedance. You rotate, basically you rotate here by 0.16 lambda. All clear? Any questions? And then the question asks you to find the input impedance of the generator, seen by the generator. And this impedance is going to be 0.3 Z in is going to be 0.3 minus 1.58 J, which corresponds to I think it's 15 ohms, 15 minus 79 J ohms, 79 point something, 79, yeah, J ohms. And that's the impedance on the input of the cable, basically. And then the next question, the last question, is like, I don't remember the number, like it's like 4. It asks you for V in on the cable. Basically, in steady state, this is going to be just the voltage division of your VG times your Z in over Z naught plus Z in. Okay, which is going to be 0.78 volts and angle, I think angle minus 28.7 degrees, I think, volts. That's a phasor. Like we're going to have some phase shift and some like reduction in amplitude. Okay. And all good. Okay, we have half an hour left for some extra things. So I want to go through 2 things. First, I want to show you how to do like Smith chart matching with stubs, because I think a lot of people have problems with this, at least I suspect. Let's say, like, let's just like pick any random point, like a point here. No, that's on the unit circle. That's a bad point. A bad point. Let's look here, for example. Let's say this is our load impedance. How do we match this to be like 50 ohms, right? Our Z node is 50 ohms. I'll just write this here, 50 ohms. In general, there are many ways to do impedance matching. You can have like you can add a series impedance, a parallel impedance, like or whatever. So I'll go through two things. One, add a series capacitor, or like something of this sort. And two, add a parallel element, basically a parallel stub. So you have your cable to your Z load. And then you add the stub to it. Either like shorted or open. And this your input, right? And here you also have a transmission line and UZL, right? So the first thing you do when you do impedance matching, you try to bring your impedance to unit circle, is the unit impedance or unit admittance, right? If you want to do a matching with the series component, you want to have unit impedance because you're going to add impedance in series. If you are going to match with parallel admittance, you're going to bring it to a circle of unit admittance to add components in parallel to it. So in the first case, in this case, you're going to add a component in series to it. So what you want to do, you want to bring this to the unit circle of impedance, to this one, right? You are going to rotate, yeah. Okay, this is your line. How long this is? Yeah, I'm just going to like eyeball it roughly. And this is going to intersect the line at somewhere around here. So this is going to be a point of intersection. So this is a section, this AB is our coax in cascade with our system. Like this is our AB. This is the length of cable. We try to bring it to the unit circle. And then we go from here to the origin. By here we add a series capacitance. How do you know? Because here we have a negative J X X. Here we have positive JX. The upper side is positive reactive impedance, and low part is negative reactive impedance. So this part is capacitive. This is a capacitor. This one is inductor. And when you go down along those lines, when you go down, you add a series capacitance. If you did it this way, you will add in a series inductance. And you can see that you need to add a lot more series inductance than series capacitance, because our load is inductive to start with. And actually, what you will see that by adding a series inductance, you can't really go there. You can only go to the origin here. You can't really go like any further. To do like the full rotation, you need to have a series stop, because it can change from capacitive to inductive like impedance. Any questions on that? Okay, that's the first one. Now imagine that you are trying to do it with a parallel stub. That means that you need to get to the unit admittance circle. You need to get to this circle, to the blue one. And that is the beauty of a double current one, because you don't actually need to flip the chart to do it. You can just like rotate it here. Let's have this section of cable from A to B. And then you do that, right? This section, it adds inductive admittance. That means we are adding a shorted stub. If you want to have have a short length of stub. Or we can go the other way around by adding an open stub, but we need to have a longer stub to do this because we need to go like a full talk around. And the way you find this length, you can see like here, like I'm just going to delete this and make it more neat. You go down here, you can see that this point is roughly minus 1.6 J. You want to add a stub which has an admittance of plus 1.6 J. So you go from, if you're trying to have a shorter stub, you go from short circuit, which is here. I'm just using the blue color to make it easier to see. This is our short, right? We short, we have 0 impedance or infinite admittance, and we rotate it until we get to 1.6, right? And this is our length of our stub, from 0 to what it is, 0.09 lambda, basically. So this stub should be 0.09 lambda long. If you wanted to make it a shorter stub, if you want to go like, you want to go that way, right? I draw it very badly. Want to go like this way. Well, you start from an open and go the full way around it until you reach the same 1.6 J. And this is going to be your like, it's going to be like a half lambda plus quarter lambda plus 0.09. This is going to be like 0.59 lambda. Okay? All clear? I don't think there's going to be a question like this in the final exam this year, but there was a question on impedance matching in 2019 exam. So there is a possibility that you will have to do this. And you will have to do it on actual one-sided chart. So you have to actually rotate it around like a few times to do this. Yeah. Any questions about this? You won't be. You'll be even just normal like, and you have to rotate it around to kind of essentially what the rotation does. You use one side as impedance one, and you rotate it and use this one as admittance one. But here you have the both of them at the same time, which is a bit easier, I think. But it requires color printing, and I don't think our lecturers are keen to spend money on color printing for our exams. Yeah. Okay, so what else? Yeah, I think that's it. Yeah. So what else can we talk about? You can okay. Do you guys remember when we did wave, guys? We had the thing you have phase phase velocity and the group velocity. Do you understand why phase velocity is greater than speed of light? Okay. I will give you an example why this is a strange topic to understand. There's an effect I don't remember how it's properly called. I think it's called EFS or something. Where you have if you have imagine you have this is ground. This is just an example to show what I mean. Just a pretty removed example. You have ground, right? This is ground, and here you have ionosphere, the lower layer of ionosphere. And here you have a small storm cloud, and you have a lightning, right? And what this does, lightning creates as a very sharp pulse of pulse of electric field. Basically, it creates a wave, electromagnetic wave, which looks basically like a step function. It looks like the profile looks like something like almost like a step function. Way this rise time is it's order of hundreds of nanoseconds. And so this the pulse propagates out and then hits the ionosphere. And what happens is that the intensity of electric field in the pulse is enough to ionize the gas in the ionosphere, at least more than at least more than this already ionized. And what you get this ring, like this like glowing ring above the storm cloud. And you can actually observe it like if you have a sensitive enough camera. And what happens is that this wave travels at the speed of light. It travels at c. But if you stand here with the camera, right? And you try to film this glowing ring above the storm cloud, you will see that it's going to spread much faster speed of light. It's going to spread like from 2 to 5 c. And which is a paradox. You can actually see a glowing ring which spreads faster than the speed of light. Why? Because this thing which actually moves is the wave. But the point of intersection of the lower layer of ionosphere with the ring, with the wave, is a point which moves tangentially to the wave front. And what you see is this is a tangent to the wave front, and it moves apparently faster than the speed of light. But actually, there's no paradox here because information does not get transferred from one point to the next. All the information is transferred from the storm cloud, right? So this speed of propagation is actually less than c. Do you see where I'm going? There's no transfer of information. If you look closely, this ionized ring, it moves here. There's no information transfer from this point to the next point. The information is transferred from the origin of the wave to each of the points consequentially. And this speed is less than c. Actually, it's equal to c in this case. And if you go back to the waveguides, if you just this is just like a bit of an aside. If you have a waveguide, right? Essentially what you have, your waves are moving they're moving at angle they're moving obliquely to the waveguide walls. And if you look at longitudinal direction, this wavefront apparently moves faster than c along that direction. But actually information gets transferred like this. And actually the path that wave takes to this point, for example, is not directly here. It is actually from here and then gets reflected. So overall average speed is less than c because the wave has to travel a further distance than just a straight line to the point. Do you see? If you were to output a pulse, if you had a waveguide, and if you were to output a single pulse, it would move like here, reflect, and get here, for example. And the path of the wave is this length. And actually, if you look at the cross section, this point is apparently going to move faster, slow down, and then again move faster. And what happens here is that the overall length of time is longer than it should be if it were at speed of light. So essentially, the velocity of the wave is group velocity, and phase velocity is just an illusion caused by the way you look at things. Do you understand it? Are you sure? All good? I have another 15 minutes. Do you have any questions about the course at all? What numbers for what?
I don't know. But when I'm looking at it now, question where this I feel like I used the wrong. I used that.
Oh, okay. If you use R equal 1 circle, then you will get a series stub, not a parallel stub. And actually, you can match with series stubs, but it's usually less convenient because you have to have a cable in series with another cable. It is asking for parallel.
Yeah. Parallel one. I did it with the R equals 1 circle.
If this is your point, and you try to move to the R equal 1 point, if you try to move here, sorry.
Yes, it is the R. creating
If you like, if you do what we're trying to say, if you did this like to the r=1 circle, and then you moved here, right? You are essentially adding a series step. That means that you are doing something like this. You're adding a step in series with your sin.
like the whole thing. Need to do with the G when you're trying to find the parallel stuff. The G equals 1. But I matched the circle with R equals 1. Hey, you still, okay? You still get it for it. I did both. I did one.
Actually, if you're not sure how you did it, like whether you did correctly, there are some simulation programs you can use to verify your answer. Like, as the spice cannot simulate it, like, I don't think the spice can simulate this machine, but there are others, like some other packages. For example, there's one called RFSim99, like RFSim99, or like there's like this one called how it's called, quite universal quarks is like it's CS or something like it's like quite universal circuit simulator. There are a bunch of those. Like you can like just look it up and and simulator do simulation and verify whether your assignment matching is correct or not. Yeah, I think it's time to finish. I don't really have like anything else to talk about. So like if you don't have any questions, then okay. Is it like huh? What is this?